Hello, this is Ms. DB, and today we're going to start Chapter 12 on sequences and series, and our first lesson is just an introduction to sequences. We're going to do this assignment in two parts. Our first part is going to be focusing on finding the nth term of a sequence. In our second part, we'll work on writing rules for those sequences. So we're going to start with, here's some information about Fibonacci sequence. In 1202, Italian mathematician Leonardo Fibonacci described how fast rabbits breed under ideal circumstances. He noted that the number of pairs of rabbits each month, and he formed a famous pattern called the Fibonacci sequence. So that's just some background about sequences. A sequence is an ordered set of numbers. Each number in the sequence is a term of the sequence. A sequence may be an infinite sequence that continues without ends, like ... such as like the natural numbers 1, 2, 3, 4, no end, or a finite sequence that has a limited number of terms, such as 1, 2, 3, 4, with those brackets around it, meaning that they have a beginning and an end. When you see A with the little sub n after it, we read that as A sub n. All right, so here's some more information about sequences. You can think of a sequence as a function with sequential natural numbers as the domain, like 1, 2, 3, 4, and the terms of the sequence as the range. So values in the domain are called term numbers and are represented by n. So that's like the x. Instead of function notation, like a with parentheses of n, a of n, sequence values are written by using subscripts. So the first term is a sub 1, the second term is a sub 2, and the nth term would be a sub n. Because the sequence is a function, each number n has only one term value associated with it, a sub n. So it's like for each x there's only one y, but for each n there's only one a sub n. All right, so we learned about arithmetic and geometric sequences in a previous course. Most likely you did this in Algebra 1. So we're going to learn about some others in this chapter, as well as more about arithmetic and geometric sequences and series. This is just a review of the arithmetic sequence from the Algebra 1 book, and that has a specific, in order to find the nth term of it, you can use this formula a sub n equals the first term, a sub 1, plus n minus 1, that's the term you're looking for, that's n, times the common difference. So how much each number is increasing by is the common difference between terms. And there's some other information here that this is how they came up with this rule. Geometric sequences, those are also functions. So again, here's what we're talking about, the domain and the range. So the position here, 1, 2, 3, 4, and then this is the term. So the first number, a sub 1, is 3, and the second, a sub 2, is 6, and the third, a sub 3, is 12, and so on. The input is the term number, and the term itself is the output. To find a term in a geometric sequence, we're going to multiply the previous term by r. So to find a sub n, you take the term before it and you multiply by r. Now that is not going to give you any term. You have to know the one before it to do that. But that's kind of the pattern for geometric. Fibonacci, we talked about that earlier. This is what that one looks like. The term number, these are like your x values. Here, let me write that on here. These are like the x values, and these are like the y values. So if our term number is 1, the term value is 1. When the term number is 2, the value is 1, and so on. This is the Fibonacci sequence. So in this sequence, you add the first two terms together. So 1 plus 1 is 2. And every term after that is the sum of the two terms before it. So you take 1 plus 1, and that equals 2. And then you take 1 plus 2, and that equals 3. And then you take 2 plus 3, and that equals 5, and so on. So that's a different kind of series. It doesn't follow the pattern of arithmetic or geometric. And this is called a recursive formula. A recursive formula is a rule in which one or more previous terms are used to generate the next term. That geometric one that we looked at was the same thing. It was recursive. We looked at the previous term and times it by r to get to the next term. All right, so now we don't know if this is arithmetic or geometric or Fibonacci or anything else. It's not a particular pattern that we know of, and that doesn't matter because we can still use a recursive formula to find the terms of it. Now in this one, the first term is given. It says that a sub 1 equals -2, so that one we already know. And we only need 4 more after that. Now they give us a pattern to use. It says that a sub n is equal to 3 times the term right before it plus 2, and it works for any value greater than or equal to 2. Now they already gave us what a sub 1 was, so we just plug that in. We can use a table here. The second one, when n is equal to 2, we plug it into this formula. Now what is a to the n minus 1, sub n minus 1? That's this value. So that goes here. So 3 times -2, that's -6, plus 2 is -4. Now we use this value for a sub n minus 1. And we take 3 times -4 is -12, plus 2 is -10. And then we take this value and plug it in. So we keep doing that. That's what recursive means, that we use the previous term over and over and over again to generate our values of the sequence. So that's our first 5 terms are -2, -4, -10, -28, and -82. All right, let's look at another example. We're going to find the first 5 terms of the sequence. So we're going to use this recursive formula right here. This is our formula. So this is the part that they put in the table right here that matches. The a sub 1 is given. So we put the term here, that's 1. And when we plug 1 in, you don't have to use the formula. So you don't put 1 here because you'd get a sub 0, and we're just starting with what they give us. They give us the first one is -5. So for our second one, that's when we start doing this. So our second one, we take this number, -5, and we subtract 8 from it. And when you do that, you get -13. Now we're going to use the -13 and subtract 8 from that. And that gives us -21. And then we're going to use the -21 and subtract 8, and we get -29. And then we use the -29 minus 8, and we get -37. So our first 5 terms are -5, -13, -21, -29, and -37. Here's another example. First one is given, so don't try to use the formula for the first one. Just put that when a is 1, a sub n is 2, because they give you that. That goes here. Then we are going to start using the recursive formula that says you take -3 times the term before it. So the term before it is 2. So we take -3 times 2, which is -6. And then we use that to find the next term. So you take -3 times -6. This is the part that we are, each time will be the term before it. And we get 18. Notice that a negative times a negative is positive, so now it was negative, and now it's positive. This one's going to flip back and forth. And then we take -3 times 18 is a -54, and then finally -3 times -54 will be a positive 162. So this column here is the first 5 terms of the sequence. Here's some problems from your worksheet like this. So you're going to do the same thing. You can use a table, or you can just write it out on scratch paper and put your first 5 terms here. Let's do number 9. Number 9 says a sub 1 equals 2, so I'm going to put that right there. Then after that, I'm going to use this, which is 1 minus 2 times the previous term. So when you see a to the n minus 1, that means previous term value. Okay, so for when n equals 2, I'm going to use 1 minus 2 times 2. So 1 minus 4 is -3. And then for when n equals 3, I do 1 minus 2 times, and then I use this again, the previous value. So that's the same as 1 minus a negative 6, so 1 plus 6, or 7. And then for 4, I go 1 minus 2 times, now I plug in this value. So 1 minus 14 is negative 13. And then for the fifth n, I use 1 minus 2 times negative 13, this value, and that would be 1 plus 26, which is 27. So my first 5 terms for number 9 would be 2, negative 3, 7, negative 13, 27. So these numbers here do not get plugged into the formula. They tell you what term we're on, and these are the values that will get plugged into the formula, into the next one. Each time they'll go to the next one. Let's look at number 10. Number 10, I'm going to use the same table, except this time my formula, my recursive formula, is the previous value, that's what this is, squared plus 1. So I take the previous value and I square it, and then I add 1. So I start with a sub 1 equals 1. So my previous value right away for this row, my previous value is going to be the 1. So I take 1 squared plus 1. Well, 1 squared is 1, 1 plus 1 is 2. Now I have to take the previous value is 2, square it, and then add 1. So 2 squared is 4 plus 1 is 5. Then I need to take that previous value of 5 and square it and add 1, and so on. And you keep doing that as long as you need to. So every time the previous value, previous term value, is what you're going to use in the next row. So this matches, and this matches right here, and this matches this. So the next time you're going to be using the 26 squared plus 1. So it's going to get super big, super fast there. All right, now we're going to use an explicit formula. So instead of looking for the term or needing to know the term before it, with this formula, we can just find any term that we need to. And they're not going to tell us what a sub 1 is. We got to find a sub 1 along with our other ones. So in this formula, we have a sub n equals 3 to the nth power minus 1. So the first thing that we're going to do is find what we get when n equals 1. So we put our table up, and I see they filled it in already, but we start with 1, so n is 1, and I go 3 to the 1th is 3, minus 1 is 2. Now I don't have to use that value. In an explicit formula, you don't take this and put it in here. Don't have to do that. In this formula, we just use these values in our equations. So now I take 3 squared for n, minus 1. 9 minus 1 is 8. And then I use this value right here. 3 to the 3rd, that's 27. 27 minus 1 is 26. And then here's the 4th. 3 to the 4th is 81. Minus 1 is 80. And 3 to the 5th is 243. Minus 1 is 242. So make sure you know whether you're using an explicit formula or a recursive formula. A recursive formula always has an n minus 1 as the sub part. It will always have an n minus 1. An explicit formula will not. It will just have the n being used in the formula. You can use Desmos to check your work on explicit formulas. We'll look at that in a minute. In this example, is this an explicit or a recursive formula? It's explicit if it just uses n as a variable and does not use the n minus 1 as the sub script part. So this is an explicit formula, and we'll solve this just like we would with any formula. We take our values of n and plug them into the equation and find what we get. So in our first part, we would take the n equals 1, and we do 1 squared minus 2 times 1. So 1 squared is 1, minus 2 times 1 is 2, so 1 minus 2 is negative 1. Then we use 2 for n, so we have 2 squared, which is 4, minus 2 times 2. 4 minus 4 is 0. And then we use 3 for n, and we get 9 minus 6. 9 minus 6 is 3. And then we use 4 for n, so we have 16. 4 squared is 16 minus 8. 16 minus 8 is 8. And then we use 5 for n, and we get 25 minus 10, which is 15. So this has generated our first 5 terms of the sequence. If you have a graphing calculator like a TI-84 or a TI-83, you can enter this into the table format, and you can generate this, and you can see your table of values will match this table that you generated. And you can do it in Desmos too. Like I said, I'll show you that in a minute. All right, so here's just another example using the formula 3n minus 5. And we get, when n is 1, we get negative 2. When n is 2, we get 6 minus 5 is 1. When n is 3, we get 4, because 9 minus 5 is 4. And when n is 4, we get 7. This is an arithmetic sequence. Each time you're actually, once you find what the first value is, each one of these is plus 3, which you could also use to kind of check your answers as you go. And again, you can use a graphing calculator to check your table of values and find them even. I did make a really short video on how to use Desmos to generate the sequences. And I'll show you that.